as a subcontractor, we had the University of Southampton. So the results that I'm going to show you have been obtained partly by ourselves and partly by Hugh Lewis in Southampton. The idea underlying the study is that, as everybody now realizes, fragmentation in Earth orbit will represent the major source of debris in the future. In the past, as you know, most of the population of space debris in Earth orbit was produced actually by explosion, not collisions. But as the event of Iridium and Cosmos told us, now collisions are becoming, will be the major source of fragments in the future. So the idea of the contract was to study what kind of consequences should we expect from collisions in the future, depending in the region where they will be happening. What are the main, most dangerous regions in space? Okay, and so since the present distribution of objects in Earth orbit are definitely a good proxy to tell us where the collisions will happen in the future, we started by identifying representative objects in a specific region of space to fragment. So the main idea of the work done in the contrast was that we were running the long term. We simulated the long-term evolution of a space debris population under a reference case, and I will detail on that later on, showing what will be the reference, the standard evolution of a space debris population for 200 years. And on top of that, we assumed that a specific epoch in time, specific fragmentation would happen in space, and we would compare the evolution of the population in these cases. This is the orbital distribution in terms of inclinations in the major axis and eccentricity of the initial fragmentation that we assume took place in Earth orbit. So we had, as you see, the blue dots are the fragmentation happening in low Earth orbit, that is in LEO. This is the major axis, and the stars are and the red stars are the fragmentation that we simulated in the geo region. Since the most crowded and most dangerous zone is LEO, of course, we sampled much more the LEO region than the geo region. So we had a number of objects fragmenting at different inclination, mostly, of course, on nearly circular orbit. And then we had a few fragmentation simulated in high eccentricity orbit, like geostationary transfer orbits. To make this long-term evolution, we basically used two different models, two different comprehensive models, able to simulate the evolution of the whole population of space debris for a long time span. The two models is the model. Number one is the model called STM, semi-deterministic or space debris mitigation model, in its current 4.2 version, which was developed in Pisa and now in Florence in the last decades. And the other model is the damage model, which was developed in Southampton in recent years. The STM model is a large software suite in which you take an initial population of objects in Earth orbit and evolve them under different source and sinks terms. Basically, the source of objects in the model are launches, explosions, and collisions, and I will detail a bit on that later on. And then a number of strange events that happens in Earth orbit, like the release of particles, lag particles, when you use solid rocket motors to boost the upstage in Earth orbit, or release of, for example, non-energetic release of drops of liquid coolant from nuclear satellites whenever you deorbit the nuclear reactor of the spacecraft. And then the sinks, unfortunately, the only sinks that we have available is the atmospheric drag for low Earth orbit, and then there are some active maneuver that you can perform with this post-mission disposal of spacecraft at the end of their lifetime. The model can account for a number of things like collision avoidance procedure and so on. All the orbits of the objects, of the largest objects, are accurately propagated with an orbital propagator which accounts for all the main perturbation, I think, on the satellite. So it's a very large and very complex model, and I can't enter in all the detail, of course. Just a few algorithms inside the model. Inside all the particles are propagated, and inside the model we check for crossing of the particles to establish if a collision, if an accidental collision is taking place. Of course, since you have to run the model for 200 years, you cannot afford to have a real checking of all the orbital crossing, deterministic checking of all the orbital crossing in the same ways that is done on an operational basis, for example, for the International Space Station. Of course, you have to rely on a statistical method, and the method that we are using is a method that is called Cube, which has been developed by JCU of NASA Johnson Space Center, and it's based on a uniform sampling of the system in time. To cut a long story short, what you do is you divide the circumterrestrial space in cubes, in Cartesian coordinates, which is not the optimal choice, but it's very convenient from a computational point of view. And then you take samples of your population in time at a given interval of time delta t, and basically you freeze the population at every delta t time and check if two objects lies in the same cube. If the two objects lie in the same cube, within that small cube, which is normally something like 10 by 10 by 10 kilometers square cube, you apply a simple particle in a box model, and with that, if you sample enough in time, you have a statistical representation of your collision probability. And then you use a Poisson extractor to check if a collision is actually happening or not within your cube whenever two objects lies in the same cube. It has been proved that this method is actually very effective in computing collision probability. It is also computationally effective. I repeated the slide just to tell you that there are a lot of models within the code, and a lot of models which are only partly under your control. When I mean partly under your control, for example, there is, as I said, there is the collision, which is a stochastic process basically. There are, for example, you have to forecast the launches, the traffic in space for 200 years, and this is of course something which is close to impossible, because who knows, who could predict in the 60s that the Soviet Union in 1989 was collapsing, and the launch rate of the Soviet Union would collapse from about one launch per week to just a few tens of launches in the year. So it's pretty difficult. Then you have, for example, to model the atmospheric drag. To model the atmospheric drag, you need an atmospheric model, which are very well developed. But the atmospheric model relies on the prediction of the solar flux in the next 200 years. And we know that the solar flux has, for example, a periodicity of 11 years, but within these 11 years, it's far from being a sinusoidal thing. So there are a number of uncertainties in this model, and you have to cope with this, trying to do sensitivity analysis and so on and so forth. I will skip this because we will talk about this in the next hour, so I skipped talking about the breakout model, which is, of course, at the core of the model, especially for a study like this, where you are interested in the effect of fragmentation in space. So you need a model which tells you what happens when a spacecraft is hit by a particle at 10 kilometers per second and is fragmented. It is the mass distribution that comes out of this event. And we will talk extensively about this in the next hour. The other model, as I told you, is the model which is called damage, which was developed under the funding of the United Kingdom Space Agency starting from the year 2000, more or less. And it's, even though they are completely independent, the underlying idea is more or less the same. You have an initial population, you have a number of models, you propagate the population and so on. And what is important is that as most of the codes around the world, SDM and damage share the same fragmentation model, which is the NASA breakup model. And incidentally, also damage used the same algorithm, a similar algorithm for the evaluation of the collision probability in orbit. As I told you, to establish if a collision is actually happening within a cube, you are using a Poisson structure to determine the occurrence of a real event out of a statistical distribution. So, for this very reason, we have to rely on Monte Carlo procedure. That is, to have an evolution, a future evolution, a reliable future evolution, you cannot run the model once, but you have to run the model in Monte Carlo fashion for a number of times. And this comes, and here comes an important point that you will notice in the next slide. That is, of course, what I will be presenting are average evolution out of a number of Monte Carlo runs, which can go from a few tens to a few hundreds. And just to show you the variability, the stochasticity of a problem, this shows you, it's very small, I'm sorry. This shows the number of objects in a simulation with the same initial setup as a function of number of runs. This is 100, and this is the range. So to say that there is a very wide distribution of occurrences of final number of objects in your environment after a simulation of 200 years if you run the code for 100 times. And as you see here, you cannot really fit a Gaussian in here. There is some hint of it, but it's not really a Gaussian. Probably if you would be able to go to 1,000 runs, probably you might obtain something which resembles more a Gaussian. But the message here is there is an intrinsic variability and an intrinsic stochasticity in this kind of models that you have, again, to cope with. So as I mentioned, we have an underlying reference case against which everything will be compared. We have a reference evolution, and the evolution where we add a single fragmentation will be compared with this evolution. The setup of this reference case is as follows. We take all the known objects in space larger than 10 centimeters from the ESA master model, which is for those of you who are not familiar, is a model made by ESA in the last few decades, where they basically take all the known objects, all the observed objects in space larger than a given size threshold, and then add all the objects that were supposed to come from fragmentation event in the past. So this is, you can see, and you have an ASCII file with all these objects. So this is the most faithful representation of the population currently in orbit. Then we have, as I mentioned, you have to assume a launch traffic for the future, and the current fashion is that you take, of course, the launch traffic of the past decade, more or less, and you indefinitely repeat the traffic for the next 200 years. The traffic model of SDM is much more complex than this, But as I mentioned, it's very difficult to make an accurate prediction of a future launch traffic. So this is seen as a reasonable, understandable option. Then, of course, there are a number of technicalities. For example, we assume that every satellite will be active for 8 years. The satellite will be station kept in an operational orbit for 8 years, and after that it will be released, or it will become actually a space stability orbit in the Earth with no control possible. We assume that for every mission which ends its operational lifetime, we apply the so-called post-mission disposal. Post-mission disposal means that at the end of your mission, you move your satellites from the operational orbit to an orbit which will survive under the effect of air drag for 25 years, the so-called 25 years rule. But since this maneuver is not performed by everybody who owns the satellites, and it's not always successful, we assume that only 60% of this maneuver are successful. We assume that there will be no more explosion in the future, which is something we are approaching actually. The number of explosions, or at least of important explosions, which model and shape the population in the past are now decreasing. So this is again a reasonable assumption. We assume no collision avoidance maneuver are performed. We could simulate that, but since the collision avoidance is not a common practice these days, we prefer to have a reference case which do not take into account that. Okay, we use it, as I mentioned many times, with an breakout model, and the projection time is 200 years. And the solar flux is averaged over last cycle, and it's a variable of 11 years periodicity. So this is the average evolution of a reference case. And this is the blue thick line is the average over the 50 Monte Carlo runs that we made, and the thin blue lines are the 1 sigma variation of this long-term evolution. So this is number of objects as a function of time over 200 years. As I mentioned, we were using two codes, two completely independent codes. So for that reason, we were forced to initially compare the two codes to see that they gave a reasonable agreement over 200 years. And then so the blue line is the evolution with the SDM code, and the red line is the evolution with the English damage code. And as you see, the two, after 200 years, with all the events, all the simulation made, they have a very reasonable agreement well within the 1 sigma variation of both codes. This is the variation of STM, this is the variation of damage.
Alessandro, why all those oscillations?
This is a solar flux variation of 11 years.
Which is more marked
yes.
with one model.
Yes, so that's the average procedure which makes this shows again a similar, again the result of the long-term simulation, but now the objects within the simulation are divided in classes of watching, type of object. The red curve, the solid curve refer to SDM, and the dotted curve refer to damage. And the red curve shows the time evolution of the fragments present in space at the beginning of a simulation. Fragments, and you see that these are the old fragments, and you see that they decay because they were present there. And this is telling you that the orbital propagator of the two codes behave in a very similar way. That is, we take the same initial population, then we evolve it for 200 years, and they end up more or less in the same place. So that the atmospheric model and all those kind of things behave very similarly. The green curves, they show the number of impacts. That is the spacecraft, the real spacecraft, and this accounts for the traffic. So these are the new spacecraft that are injected in the simulation. Some with all the intacs that we had at the beginning of the simulation, and again the two models compare very nicely. And finally, the blue curves shows the number of new fragments generated by the new fragmentation happening during the run of the model. And again, the comparison is very nice between the two poles. So as you see already, there is a consistent increase in the number of fragments, of new fragments, starting from 0 point, the beginning of simulation, over 200 years. And it goes to about 16,000 new fragments generated in the 200 years time span. Another point you have to compare is the number of the average number of fragmentation happening in the 200 years simulated time span with both the codes. And again, you see, and this is a check for implementation of the collision probability algorithm. And you see that in both the codes you have about 40 fragmentation, that is collision that completely fragment the target in the next 200 years. And these are the 1 sigma bars in green. So this is another important message. On average, in the next 200 years, we are seeing in our model 1 fragmentation every 5 years. These are already in the reference model without the new fragmentation that we are supposed to check. And this is the location of all the fragmentation that are happening in the next 200 years. And as you see, they are clearly related to the present distribution of objects. These are the peak where already now we have the largest distribution of objects in space as a function of altitude. That is, we have a well-known peak of objects at around 800 kilometers and 1,000 kilometers. And here is where most of the collision of the fragmentation in the next 100 years, of course, will take place. And another hot zone is the one around 1,500 kilometers of altitude. In terms of the mass distribution of the fragmentation, already in the reference case, again, most of the fragmentation involve targets, spacecraft in the 1-2 tons regime. But we have a number of fragmentation in the several tons regime up to 8 or 9 metric tons of targets fragmented. Okay, this is the reference case. One of the main motivations of the contract for ESA was MVSAT. I guess most of you are familiar with MVSAT. MVSAT was a huge polar platform launched by ESA in a sun-synchronous orbit. It's an 8 tons spacecraft which gave wonderful measurements of the atmosphere for atmospheric science for a number of years. And unfortunately, it ceased operation. They lost contact with the spacecraft a couple of years ago before being able to do any deorbiting maneuver to the spacecraft. And this spacecraft is actually located right there. Surprise, surprise. So the idea is, if there is anything, the main idea underlying the study was, is there anything going to eat MVSAT in the next future? MVSAT is an altitude, you cannot see probably, it's at an altitude of about 900 kilometers, so it will last for about 100 years without re-entry. So, and the collision probability for MVSAT in this long time span is approaching 1. That is, it's most probable that it might suffer a fragmentation. So the first simulation that we did was to assume the fragmentation of the MVSAT as being hit by a projectile of about 6.5 kilogram at 10 kilometers per second, which is able to theoretically fragment MVSAT. So again, we are running the same model with the same assumption as in the reference case. The only difference is that at selected epoch, 2020, 2070, 2095, we are assuming that MVSAT is fragmented by the above-mentioned collision. This is not a stochastic collision, this is something ad hoc introduced in the model. So again, the blue line is the reference evolution with STM. The red line shows the number of objects as a function of time in the case in which we assume that MVSAT is fragmented in the year 2020. The magenta line, the evolution if we assume that MVSAT is fragmented in the year 2070, and the black line we assume that MVSAT is fragmented in 2095. You see immediately that what happens is that the number of course, we have a sudden increase in the number of objects because we are fragmenting 8 tons of material in Earth orbit. But if you notice, the long-term evolution of the 200 years falls all within the same uncertainty, 1 sigma parts of the reference evolution. That was made with STM. This is made with damage, and again you have the same result. A huge jump over here at the beginning when you have the fragmentation of MVSAT, but then the final evolution is almost undistinguishable from the reference evolution. This is the number of the total number, the cumulative number of collisions in the 200 years, again comparing the reference case and the case in which MVSAT is fragmented, a different epoch, and again you see that the number of fragmentation are all well within the 1 sigma bar, and are all again around 40 collisions over 200 years. So what is this telling us? The naive conclusion is we don't care if MVSAT is fragmented. Of course, this is not the whole story, but indeed, the simulations are telling us that the process of the long-term evolution of a population is a stochastic process which is dominated by the large number of fragmentation, large fragmentation as we saw, involving spacecraft between 1 and 9 tons, happening once every 5 years. So what happens is that the fragmentation of MVSAT, even though MVSAT is a very large spacecraft, is just one of the many. It's not the event which will alter, which will change the long-term evolution of a population of debris as we know it for the next centuries, but it's just something which statistically is almost irrelevant. That is something that will not drive the future evolution of the space debris population. As I showed you, MVSAT was the main study case, let's say. We devoted quite a lot of time in simulating the MVSAT case, but then we had, as I showed you in one of the first slides, we had to sample most of a LEO space, of a circumterrestrial low Earth orbit space. So we simulated a large number of events, and I'm not showing only, of course, all of the simulation, because otherwise those still awake will fall asleep as well. But I will show some specific case. First, I'm showing you the most extreme case, if you want. This is the only case that we simulated where the final distribution, the final number of objects is on the limit of the statistical significance of the Monte Carlo procedure. That is, the only case is in which the final number of objects remains very well distinct from the reference case. So this is the fragmentation of a huge spacecraft, a rocket body, actually a Russian rocket body, CN2, which is an 8-ton spacecraft fragmented on a very high orbit. This is an orbit of about 1,000 kilometers of altitude, that is well above the dense layers of the atmosphere. So it's every fragment is very long-lived. And this is the only case in which you strikingly see a difference. To show you the importance of the location of the event, this is again an 8-ton spacecraft, but this event is happening about 300 kilometers below the previous event. And as you see, the long-term resolution is completely different. Now you have a sudden jump of a number of objects, but most of the fragments soon re-enter the atmosphere, and the final evolution is completely undistinguishable between the reference and the fragmentation case. So it's very important where the fragmentation is happening. The mass is an important factor, but the altitude of the event, of course, is driving the long-term evolution of a clouded fragment. This is an intermediate case. This is a spacecraft of 4 metric tons fragmented in sun-synchronous orbit in an altitude of around 900 kilometers of altitude. And again, you see that there is a transient phase where you have an increased population, but then the final evolution is indistinguishable from the reference case. Another similar case. This is to show you. These are the same spacecraft, sun-synchronous spacecraft with the same mass. The only difference between the two cases is that the red curves show a fragmentation which is happening at 100 kilometers above the black line. So same spacecraft fragmented at 100 kilometers of altitude difference on circular sun-synchronous orbit. And again, you see that there is indeed an interim phase where the two evolution are separate, but then a chance event happening here in the black case is driving the simulation at the same place. So again, high stochastic variability, it's very difficult to predict the long-term evolution. This is telling again the same story, more or less. There is same spacecraft of 2 tons happening at different altitude, and then all actually lying below the reference case. It doesn't mean which is a plus for the environment to have fragmentation. It's just telling you that it's not possible to deterministically say this fragmentation will do this result. This very messy slide shows you a number of fragmentation of a 1400 kilogram spacecraft at very difficult in a wide range of altitude, from 700 kilometers of altitude up to 1400 kilometers of altitude. No, actually, up to about 1600 kilometers of altitude. And all the red curves shows fragmentation happening between 950 and 1400 kilometers of altitude, whereas the black curve shows the lowest one, and the green curve shows the highest one in terms of altitude. And as you can see, it's almost impossible to discriminate these two events. So mass and altitude plays a role, but it's a very fuzzy role within the long-term evolution. All that gets mixed up. So the concluding remark from all this huge number of simulation is that first, in none of the cases that we simulated at the end of a 200-year time span, there is a single evolution which lies outside the plus or minus 1 sigma reference interval of a reference case. That is, statistically speaking, all these evolution are leading to the same environment. Of course, this is not the whole truth. Of course, if we would be able to run again a huge number of Monte Carlo cases, 1,000 Monte Carlo cases, you would be able to restrict your 1 sigma bars just for statistical reason, and then you might have end up with evolution which shows a larger signature. But already this tells you that the situation is quite fuzzy. What we simulated a number of different targets with different masses, and what we saw is that all the fragmentation involving targets smaller than 1 metric ton show actually no appreciable long-term differences with respect to the reference case, irrespective of the altitude of the event. And as we will see in the next slide, the driving parameters which influence the long-term evolution are indeed a combination of the mass and of the altitude. Fragmentation, which happens in already very crowded zones like the 800, 1000 or 1500 kilometers altitude zones, seems more prone to produce signaturing events, probably because they are able to generate feedback collision with the existing very dense population in that region. So the region where fragmentation takes place is another important factor in the long-term evolution. And if we look at fragmentation, which happens above about 900 kilometers of altitude, where the lifetime of fragments exceeds the simulated lifespan of 200 years, it's even more difficult to discriminate between the results of a given fragmentation with respect to another fragmentation, even though they have different altitude. That is, above 900 kilometers, more or less everything looks the same, because there is no drag action, basically. So it's not possible to tell that the fragmentation happening at 1,000 kilometers of altitude will make more or less damage with respect to a fragmentation happening at 1,200 kilometers, because the evolution, the orbital evolution of the fragments is basically the same. So the conclusion is that we don't care. Let's everything be fragmented because there is no signature in the event. Of course, this is not the conclusion. There are indeed local effects, local transient effects, which might cause a very high risk spacecraft orbiting in a certain region. This plot shows a similar results, but now as a function of time we have the spatial density of objects in a given region of space. So we have here a fragmentation of a sun-synchronous spacecraft, and we track the number density of objects in the altitude shell where the fragmentation is taking place, that is between 850 and 950 kilometers. And as you see, in that particular region, indeed, for about 100 years, you have an environment which is strongly perturbed with respect to the reference one. Then it normalizes, but for a long time period, in that particular region, your spacecraft will be confronted with a number of fragments which might cause damage to your spacecraft. So you might be forced to do frequent avoidance maneuver in that region. This is a similar situation, again, spatial density of objects as a function of time for fragmentation of a Meteor 2 spacecraft at an altitude of about 1,000 kilometers. So seen so this is the density, the altitude shell between 900 and 1,000 kilometers. And it is again the most striking case, the Meteor 3 fragmentation happening at a very high altitude between 1,100 and 1,250 kilometers. And again, as you see, this altitude, this peculiar altitude, particular altitude shell will be forever perturbed by this fragmentation. Okay, these are already mentioned. Since we ran a very large number of simulations, we needed an evaluation norm to evaluate the effect of the fragmentation on the environment. This is the very simple norm that we use. That is the difference. You compute the difference between the number of fragments generated in the case where you simulate the additional fragmentation with respect of the number of fragments in that particular year in the reference case, and you divide by the sigma, by the one standard deviation in that particular year in the reference case, and then you plot it. And in that case, you see, for example, for the MSAT case, this is one that is above the blue line. You are above the statistical noise, let's say, And as you see, for example, in the fragmentation of MVSAT in the year 2020, you are well above the statistical noise, the statistical variation for about 40 years. And then, since MVSAT is, even though slowly, is decaying, if you have a fragmentation in later years, you have a decreased effect, which is a combination of the fact that MVSAT is decaying, so the fragments are lasting less in orbit. And at this time, the background population you have, since there are 50 years from here to there, you have a number of other chance fragmentation which happen, so the background is higher, so the comparison between the new fragments and the background accounts for a smaller peak. And so this norm highlights some other behavior. And if you take the norm and you sum it over the all investigated 200-year time span, you can come out with a single number, which we call C star, which tells you in a single number the effect of fragmentation on the environment. You are not supposed, of course, to read this, but just to show you that we computed C star norm for the fragmentation that we simulated, and here you can see all the simulation that we did. These are the spacecraft that we fragmented. These are the blue. In blue are the list of simulation that we performed with STM, and in red the simulation that we performed with damage. So as you see, we ended up simulating 45 different simulations in both year 2020 2070, so a huge amount of CPU time. And this shows you, as a function of the color bar over here, the C star values for all the fragmentation. It's probably very difficult for you to see the colors, but this is the mass of the target on the x-axis, and on the y-axis we have the perigee altitude. And as you might notice, of course, as I mentioned, here you have small targets, and here you have lower altitude. And as you might notice that you have the reddest and yellowest and more yellow color and more in this region. This is the distribution of the C star values as a function of inclination. There is less correlation, and this is a 3D plot where, of course, you cannot see anything, where you have a combination of mass, perigee versus inclination. I skipped this very fast because then we did a very simple linear feed. Here you have the altitude of the event, and here you have the C star. And this is the fit of the C star distribution with respect to the altitude, and this is a linear feed, a very simple linear feed of the distribution of the C star values. This is for the C star as a function versus altitudes, and this is the C star versus mass. There is a loose but clear correlation that is an increased value of the C star with increasing value of the mass of the target. But the best fit you have is whenever you combine fitting. If you try a fit of a C star with respect to the mass, well, divided by 10,000, just to normalize it, multiplied by the altitude of the event, the parameters of the fit increase noticeably. So there is a clear evidence that the driving factor is a combination of the altitude and the mass. If you add also the inclination in the fit, that is, you fit the distribution of the C star as a function of mass times the altitude event times a given function of the inclination. This gamma function is just the cosine inclination divided by just things, but doesn't matter. It's just basically the inclination. You see, again, the fit improves. So it highlights the fact that the driving factor for the long-term evolution are the mass multiplied by the altitude multiplied by the inclination. These are the three main driving parameters. And those were the computation made for SDN. We made the same for damage. We had to keep them separated because since in the computation of the C star enters not only the number of fragments but also the spread of the standard deviation and the two cones shows different standard deviation, it would be misleading to compare the C star with two cones, but the technicalities, the results show actually the same behavior, that is mass, altitude, and the lower effect of inclination. As I showed, we made also a number of simulations for the geo cases. As you know, the geo population is a completely different population up to now. We didn't have accidental collision in the geo region, luckily up to now. We had a number of explosions there, some recorded, some unrecorded, but most probably happened. But indeed, we have in geo a number of uncontrolled spacecraft that are left there, which are possible target and projectiles for future collision. Collisions in geo involve very different physics. They are not upward velocity collision. They are not at the level of 10 kilometers per second. They are at the level of at most 1 kilometer per second. But indeed, they can lead to fragmentation. So again, we assumed 12 different fragmentation in geo, and basically the difference between the one event and the other is that we simulated the fragmentation of different spacecraft mass in three main kinds of orbit. That is, orbits within the geo ring, that is at the operational level of geostationary satellites, that is 42,164 kilometers of altitude. A fragmentation happening in the disposal area that is a few hundred kilometers above the geostationary orbit, and then but at zero inclination, and then fragmentation happening in abandoned spacecraft, that is spacecraft which are not kept in the orbit, and then that gained inclination, that is on inclined geosequential orbits. And before showing the results, again, this shows, as for the case in I show you the distribution of the chance fragmentation events happening in the reference case, in the reference simulation for the geo cases. And again, you see that you have to check here. Here the number is 0.12. This is the average number of fragmentation happening in geo in the reference case over 200 years. And you see that, of course, the number of events of chance fragmentation happening in geo are much lower than events happening in LEO, but indeed we have a number of fragmentation happening also in geo. And this shows the same result that I showed you for LEO, but for the case of geo. Again, this is the blue line is the reference average Monte Carlo simulation with the 1 sigma variations, and the magenta, black and red lines shows the number of fragments generated when we assume a fragmentation of a 3-ton spacecraft happening in the year 2020 on different inclinations. Here you see a completely different evolution. Now, since we have no air drag, no nothing over there, basically we just rely on solar radiation pressure to get rid of some of a very high Earth mass ratio particles. All of the particles remain there, so the evolution of the cases are well separated. You don't have a mixing. This is another case of a spacecraft happening, of a fragmentation happening at a different altitude. This one, the red one, is the real geostationary altitude. The magenta line is a few hundred kilometers above, and there is basically the same evolution. This is the fragmentation of a much smaller spacecraft, 1,000 kilograms, and here you see a different behavior. Now, since we also have, as we saw, even though a few, but we have a few fragmentation in geo, the additional one small fragmentation, just 1 ton of material over there, leads to an environment which is statistically, again, undistinguishable with respect to the reference case. So the conclusion for the geo regime are different with respect to the LEO regime. that is due to the lower number of fragments and the lower number of chance fragmentation, a massive fragmentation of a 3-ton spacecraft in GEO will give a signature, a long-lasting signature in the environment. In the case of a small fragmentation of a 1-ton spacecraft, the evolution remains well within the reference case. There is basically no effect seen if you make the fragmentation in the year 2020 or in the year 2070. And there is no, here apparently in GEO, the only driving factor is the mass. There is no noticeable difference if you make the fragmentation to happen in the geostationary orbit, in the disposal orbit, or an inclined orbit, which is a bit surprising, but this is what we see. Last slide. What we learned from this simulation, as I said, we made an incredible amount of simulation. We made more than 3,600 Monte Carlo runs of this very complex code, which requires several hours, from hours to days to run. And these are only the runs which were, let's say, positive. Of course, there was a trial and error period at the beginning, so the actual number of runs performed was much more than this. And we produced more than 1 terabyte of data to be analyzed within the contract. So for the lesson for the future is that we obtain a number of results which are very important for us to study the long-term evolution of the population, but building on the experience of this contract, it will be good for the future to concentrate. Now that we have identified that the driving factor, it will be more important to concentrate on specific large fragmentation, for example, disregarding everything below one metric ton, which doesn't create almost any signature. We should concentrate on larger spacecraft, larger events, and trying to produce many more Monte Carlo runs to refine the statistical results. End of part 1.
We have time for a few short questions.
I'm just wondering if you backgrade your models, if you have tried to calibrate this projection with respect to the Iridium Cosmos, and whether if you use your models and backdate it based on historical data, for instance, for Iridium Cosmos, now given that we have 5 years, let's say, since the collision, whether the models can be calibrated in some sense with the true, let's say, evolution of the fragmentation population. Even if it's only 5 years, I assume that it can be used as a calibration tool.
Yes, we did a number of calibration of the models. If you mean the fragmentation model, you will see in the next hour that was done. It will be done. And we also calibrated the... Yes. So yes, the model has been calibrated. For example, the model has been calibrated in taking the population from 1957 and propagating it up to current date, and to see that they give a reasonable evolution of the population from 1957 to 2010, for example. And then we did a number of calibration of the models between models. For example, we did the IADC, the committee, where we take sample cases and we propagate the sample cases all together with the Italian model, the French model, the English model, the NASA model, the JAXA model, and we compare the results to see that the model give similar results. So yes, there were a number of calibration that went on in the past.
So I can just add one detail. So for instance, knowing that some of the ISS maneuvers, in the last year included Iridium Cosmos fragments that were actually detected. I don't know what the resolution of the models are, and whether you can look at, for instance, the secondary collision scenarios that emanate from the main collision, because I assume that's what's driving a lot of what's growing in the system as well is that you have the cascade going on. So you have data for cascade in some sense now as well.
Yes, in the model we can track feedback collision, that is collisions that are produced by fragments. So I didn't show the results, but yes, we can track secondary collisions. The resolution of a model is not such that we can predict, as I said at the beginning, with this kind of model, the time sampling of a cube model is 5 days. So it's behind the possibility to make this kind of analysis that is done by combo, or this kind of modeling, ellipsoids of confidence around every single object. We have the capability of doing that, but you cannot do that for 200 years of trace. But it's indeed something that we see feedback collisions.
Okay, any other question? If not, we can proceed with if you can. Speed up a little bit.
Yes. Okay, the idea here is that with your help, we will identify weak points in what I told you before. And we will concentrate on the fragmentation model. All the previous long hours was devoted to tell you the consequences of the fragmentations in space. And of course, to tell Recon the effect of the fragmentation in space, you need a fragmentation model. That is a model that tells you, given the fact that an object is destroyed, what happens to the cloud of fragments, how many fragments are generated, and the kind of fragments that are generated. This is also a common problem which is faced by people doing asteroid studies. The way an asteroid fragments has been the subject of a huge number of studies, for example, as was mentioned this morning, for the formation of asteroid families. And as a matter of fact, the first model that we used in PISA to model the fragmentation of a spacecraft was a model that was mediated from asteroid studies in the 90s. The first model was developed by Paolo Farinelli, Alessandro Cordelli, and myself in PISA in the early 90s, and was derived by a model which was studied by Farinella, Petit, collaborator, and Martelli in Great Britain to study asteroids fragmentation. So the first model that we used was actually a model derived from asteroid studies. The model that we used was working on a fundamental difference between, like in the asteroid case, from total fragmentation of a target and localized damage, what in an asteroid is a craterization event. And the threshold which discriminates between the two events is of course called a fragmentation threshold. The basic of the model, the old model, was that the number of fragments larger than a given mass m is a power law function of the mass of that mass with an exponent b. The parameterization of the collision energy is done by the parameter sigma, which is the ratio between the kinetic energy of the projectile and the target mass. And as I mentioned, we have two kinds of events where you have a localized damage if sigma is less than the fragmentation threshold, and you have the complete fragmentation of the target if this ratio is larger than the fragmentation threshold. It turns out that for spacecraft, the fragmentation threshold is between 35,000 and 45,000 joule over kilogram. Is anybody in the room who knows what is this value for asteroids? Anybody who is in ER or ESR? No? For example, not Paul, not Shulin.
It's like 10 joules or something like that for a 100-meter asteroid.
It's about one order of magnitude less. It's about 1,000 joule over kilogram for an asteroid. And the reason is why the reason is because a satellite is basically an empty structure, and it's at 10 kilometers per second, even though the amount of energy which is transmitted by a 1-ton spacecraft traveling at 1 kilometers per second, if you compute it in joules, it's just huge. The time of event is so fast that it's not possible to couple all the energy to the structure of a spacecraft. If you shoot a Coca-Cola can, or you shoot a rock, the difference, it's immediately noticed that the can is empty, so your projectile just passes through the can, breaks the can, but the number of the amount of energy transmitted to the body is less because you have an empty structure. So this is the first fundamental difference, which we learned when we made the first simulation with this model. You can use the model for asteroids, but we have to assume a completely different fragmentation threshold. Well, without entering in much detail of a previous model, which is the number of fragments, the functional form of the model was this one, where the number of fragments largest than a given mass m is given by mu, which is the mass of the largest fragment produced in the fragmentation, divided by m multiplied by elevated to the power b. The mass of the largest fragment is given by this expression, where mt is the mass of the target and ep is the kinetic energy of the projectile, and sigma is again the quantity that I showed before, the ratio between the projectile energy and the mass of the target.
Where does this come from, the last one?
From the laboratory.
From the laboratory experiments of Martelli et al.
And also
Fujiwara and so on.
Of course, you assume that the projectile is small.
Yes. Small, but enough to carry the kinetic energy. Yes. The exponent b in the fragmentation regime is given by this expression, which entails the mass of the largest fragment and the mass of the target. The characterization regime, the behavior is different, but I want to concentrate over this. So this was our previous model. It was a model that we applied for a very long time at the beginning. But it was derived initially for rocket bodies. Then, in the early 90s, beginning of the year 2000, the model which is used now appeared. And this is a model which is published in a paper by Johnson et al. In Advances in Space Research in the year 2001, and is a new breakup model which is based on observation of the big cloud in space and on a test which was dubbed Sochi.
This is valid only for satellites?
This is the satellite model.
Not for asteroids?
No, this is a satellite model. And this model was calibrated, and I borrowed this slide from JCU, from NASA, was calibrated by this single test, which was a test which was developed by the Department of Defense and NASA, and was called Satellite Orbital Debris Characterization Impact Test. It was conducted in 1992. And they took a spare satellite, this transit navigation satellite that they had at hand, which was a pretty small satellite, an old satellite built in the 70s, basically 70s, 80s, actually the 60s even. And was selected just because it was available. They didn't build it on purpose. And they shoot a projectile at 6.1 kilometers per second. They measured a number of those fragments, but not all of them. You have a huge number of fragments, so you need a lot of people doing the job and so on. So they actually measured only 10% of the fragments, then they grouped all the remaining fragments together in groups. So, and they scaled up the results. So they made an approximative, let's say, analysis of the event, of the single event. And then they say that the model was calibrated on the cloud of debris of fragmentation seen in space. And this is the list of the fragmentation that they used to calibrate the model. And the list is empty. There were no calibration clouds. The only clouds of fragments that they were able to use in space were clouds coming from explosions. There were no known fragmentation of spacecraft at the time in space. So a fundamental piece of information was missing. There was nothing to calibrate the model, and the model is a semi-empirical model, so it needs calibration. So first, uncertainty in the model. And the distribution they came out for the fragmentation model was the following. So which are the main differences between the model that I showed you before and this expression? Speak up. Should I do like in the classes? You tell me. Okay. It's first main difference is this one. It is the physical value that they use is not the mass. It's the length of the fragment. But SC is the so-called characteristic length, which assumes that an equivalent spherical object, blah blah blah. But it's the length. And why did they use the length and not the mass? Because you can observe it from space. They use the mass because they actually are developing the model from observation of cloud in space, but they don't have. But they use it they did it for explosion. So the physical quantity is the length because it's what you observe with radar. They are observing radar basically. So the length was what they get from the radar observation. And the other point is that if you remember here, you have an exponent which is b, which is a function of mu, which is a function of EP. So in the previous model, if you have a very energetic event, if you have a 1-ton spacecraft hitting a 10-ton spacecraft, or you have a 100-kilogram spacecraft hitting a 1-ton or 10-ton spacecraft, you have a different physical behavior. The energy enters. Here you have no influence of the energy of the projectile. Doesn't depend, the exponent is fixed, it's 1.71, that's it. And again, why is this? Is it a mistake or is it done on purpose? Or it is related to the fact that you don't have a complete transmission of energy. They realize that there is no complete transmission of energy from the projectile to the target. So there is a much slighter dependence on the energy of the event with respect to what was thought before. With the Knudsen, with the model we developed, a very energetic collision was basically driving the target to atomic pieces. If you have a collision between huge spacecraft, the energy was such that the spacecraft was fragmented in very tiny pieces. This is not apparently what they observed. Because indeed they had a single ground test, but that was the only public test. Of course, the military did many more tests for different reasons, but those results are classified. But apparently, from the military test, they saw that high velocity tests create larger fragments than expected. Okay, now we have a distribution of objects as a function of a characteristic length. So from that quantity, since in the end what you need is the mass of the fragment, you have to transform this distribution in a distribution of quantities that are useful for your models. You need the mass, you need an area of the object, because you need the area over mass ratio to propagate the object. So, well, in the case of a catastrophic collision, again they have a fragmentation threshold, and the fragmentation threshold of the NASA model is set to 40,000 joules per kilogram. You are supposed to use that, not to change it, because it's related to all the other parameters of the models. So whenever the energy exceeds this fragmentation threshold, you have complete fragmentation, and the mass involved in the mass that goes into fragments is simply the sum of the target and the projectile mass. Whenever the fragmentation is non-catastrophic, the mass which goes into fragments is the mass of the projectile, of course, times the mass of the projectile is multiplied by the collision velocity, and is then normalized by kilometers square in order to get a mass as a unit of measure. A nice thing to know here is that if you read the paper by Johnson et al. 2001, there is a mistake in the paper. The square here was missing. So there was an update of the model. So all the community went on simulating the non-fragmentation collision without the square over there. Luckily, the non-fragmentation events are not the driving factor for the long-term evolution. The fragmentation, you produce minimal fragments. And this mistake was spotted by a PhD student in Southampton currently, which is called a girl, it's called Letizia, and because what happened is that one of the members of the NASA JSC group published on the Orbital Debris Quarterly News an update of the model just to explain how the model is to be managed and implemented in software and so on. And she reported the correct value, the correct formula, so that this girl was studying and she noticed the difference. So she told to all the community that we were using the wrong formula, the wrong equation for about 10 years. Too bad. But of course, a lot of people reading the simulation, and luckily the long-term simulation are not very affected, are not affected basically at all by this difference, but there is some difference. Okay, then there are a number of, then the implementation of a NASA model again has to go from the characteristic length to the area over mass ratio. And this is done, since it's a semi-empirical model, it's a very cumbersome model to implement. So I will very briefly sketch. You have a distribution for rocket bodies behave differently from spacecraft, because again the structure is different. Then they discriminate a size regime above 11 centimeters and below 1.17 centimeters for rocket bodies, one for spacecraft, blah, 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 blah. And then there is an in-between region where they have no data, so they use a function to bridge the two regimes. So it's a very, very cumbersome implementation. Then, starting from a characteristic length, you derive an area over mass ratio directly from the characteristic length using a combination of Gaussian distribution of this form. Okay, no need to go into detail, but this is just to show that it's a very iterative procedure with with a lot of statistical distribution in it. So you don't have a single value for relating a length of a fragment to an area, to a mass, but you draw it from a distribution, basically.
Sorry, but all this is based on only one? That's crazy.
That's the whole story for this 45 minutes painful lecture. For small fragment, they use a single distribution, whereas both for spacecraft and rocket bodies. Whereas as I showed you, for larger fragments, you have two different distributions for rocket bodies and spacecraft. Well, the problem is that they have only one single experiment unclassified. Probably they use some information from classified experiment, and they use a lot of information from explosion clouds, and they transmit it to fragmentation clouds, assuming that some of the physics is the same, which is true or not true. Yes?
Yes, at the last IAC there was a presentation that they reproduced this experiment with the new
coming.
Oh, okay.
Then, once you have a distribution, a nearly Gaussian distribution of the area over mass ratio stemming from the distribution of the characteristic length, you compute the area attached to a given characteristic length, and you get an average value like this. And again, you see the exponent, this exponent has 1, 2, 3, 4, 5, 6, 7 significant digits. It's a single experiment. And once you have the average value of the area over mass attached to a given characteristic length, you divide that average value of the area by the area over mass ratio value that you get from the distribution, and you get the actual value of the mass. And this gives you all the information that you need. And here you don't see it because it's too thin, but this is the distribution of the cumulative distribution, the power law basically. And you see many thin lines here because since it's drawn from distribution, you have a random number generator, and here is about 100 occurrences taken from the distribution. So this is just to highlight the fact that given a mass of a target, you don't have a single distribution of fragments. You don't have a single power law, but you have a distribution of power law. So in your model, again, there is a variability for every fragmentation. Well, this is the mass distribution reconstructed from the characteristic length distribution. Then, of course, you fragment, as in the asteroids, an important information is what is the velocity of the ejecta fragments, the fragments generated. And again, this was the information that should come from the cloud in space, but they had not available. So they should derive it from the Sochi test, but the Sochi test gave no distribution of velocities for a number of reasons related to the experimental setup. It's very difficult, as we will see, to get information on the velocity. So here are two important assumptions. The velocity increment given to a fragment after the collision is assumed isotropic, and is assumed to stem from the center of mass of the target. Always. Which is most probably not the case, and we will see detail later on. So, then you implement all this mass, all this story, and you see that you have a number of, let's say that you have you are interested in fragments larger than 1 centimeter. So you have a number coming out for that equation gives you a number. I mean, how many fragments larger than 1 centimeter you have after a collision. Then you apply all the machinery, you draw all the mass, area of mass, mass, you sum all the mass, and you don't have the mass of the target. You are well below the mass of the target. You are missing a lot of mass. So in the model, now there are the prescription to add large fragments, where large means larger than 1 meter, so big fragments coming from explosion, which contain most of the mass. So again, you have 7 characteristic digits for the exponent, and then it turns out that 40%, 50%, whatever, of the mass of the target is basically drawn by chance from a very simple distribution of mass to accumulate the final mass. Again, another point. These are pictures. I don't know if you can see something I can see on the screen, but these are pictures coming from a very small experiment performed in Japan by Hanada and Liu. They shot basically a CubeSat with a small projectile at 2 different velocities. One hypervelocity impact, that is a projectile traveling at about 4.5 kilometers per second, and the lower velocity, larger projectile traveling about 1 kilometers per second. In both cases, the total the energy of the projectile was enough to be above the fragmentation threshold from the target, so they had a complete fragmentation in both cases. These are the plates of the CubeSat after the impact. Would you tell which one is the high velocity and which one is the low velocity?
A should be hypervelocity.
Pardon?
A, so the line.
This one?
Oh, you mean, okay, no, the one
This
on the
one?
left, on the left.
Yeah, from this was one experiment, this was the other experiment.
Yes,
Okay, this one was the hypervelocity. And the hypervelocity didn't pass the last panel. And again, this is related to the transmission, apparently, of a shock wave. The larger projectile, but slower, was more able to penetrate the spacecraft. And this is something that they observed also in the shielding, for example, of the space station. Large, slow projectiles are more dangerous than fast, small projectiles, even though the kinetic energy transmitted by both is comparable. So as you see, there are a number of uncertainties in the model. So what new test would you suggest, and what kind of measurement apparatus should we need? Yes?
The post-impact velocity distribution should be known.
Pardon?
The post-impact velocity distribution should be known.
Yes, it should. Okay, one, as you can see from this very sophisticated CAD image that I produced, there are another fundamental uncertainty is this one. This is a projectile traveling even impact speed, impacting the spacecraft. For the NASA model, the outcome of this collision is the same as the outcome of this collision, which is the same as the outcome of this collision. What would you expect, for example, from this collision?
You expect that if you have a cube and you impact normal to the surface, this is one thing. If you impact from the response will be very, very different.
And if you impact like this, I mean,
Okay.
if you have, assume that you have this spacecraft made like this, and assume that this spacecraft, the mass and the velocity of this projectile is not enough to cause a complete fragmentation of the spacecraft, because, for example, the sum of these two modules is 10 tons, and your projectile is just 5 kilograms at 10 kilometers per second, more or less. And you don't reach the fragmentation threshold. But if you consider this as a spacecraft, and this other one as a spacecraft, you destroy this spacecraft. You do not destroy this, because there is no transmission of energy between these two parts. So in your model, if we run the model as we run it now, we assume that this event is just a localized damage. So we produce a number of fragments which add up to this mass, not to this mass. But most probably what you should do in this case is that you should assume that the mass of the fragmented part is the whole mass of this module plus, of course, the mass of the projectile. And this makes a substantial differences. And this was never simulated, and you should probably change the result quite significantly. And in fact, so finally they had some clouds in space. Unluckily, as it might be, but for experiments, they finally had clouds in space. In particular, there was this deliberate fragmentation of the Fengyun spacecraft, Chinese Fengyun spacecraft. So this is the size distribution predicted from the NASA model, and this is these are the measurement basically of a cloud of a Fendium fragments made with different sensors. So this one goes down to about 1 millimeter and was done with the Goldstone radar, a very powerful radar antenna there in California. And as you see, actually the size distribution compares more or less reasonably with the cumulative size distribution of a NASA model.
What was the mass of the original mass of the satellite?
It's about, I guess, about 1 ton. But, I mean, the slope is similar, but this is the number. This is the number of fragments. This is borrowed again from NASA. This is the distribution of fragments produced with applying the NASA model as it is. This is the number of observed fragments. Take into account that you do not observe all the fragments. So as you see, the number of fragments produced by Fendium was incredibly larger than the number of predicted fragments. So, first point. Then we had another important fragmentation in space, the cosmos fragmentation against iridium. And here you see a different story. The NASA model goes almost perfectly well. Why? No, that was a collision as well, because it was a deliberate, it was a direct hit by a project pilot, high velocity. They were both collisions. Sorry?
The shapes, dimensions of the two space were very comparable.
It's the age. Sorry? It's the age of the spacecraft. This spacecraft was built in the same period as the transit spacecraft. It was an old spacecraft. The Fendium is a new spacecraft. It's made of different materials. They had a single test with the spacecraft which was old. And in fact, this is the cloud from Cosmos, and this is the cloud from Iridium. Simulated, observed. Iridium is a new spacecraft. It's made with different materials, so it has a lot of MLI material, new materials, carbon materials, which was, whereas most of the, for example, most of the satellites at the time were built either aluminum or steel. So having a single test with an old material, so what do we need in the new test? We need a spacecraft which is similar to the spacecraft that are launched now. And in fact, well, if you divide by 3 the error over mass ratio of the observed fragments, to basically match the NASA model, which means that the new spacecraft are built with more fluffy materials, more materials which has an area over mass ratio higher than the old spacecraft, which is a good news actually, because if you have an higher area over mass ratio, you last less in space because the drag is more effective. So, as Clemens/Donald was mentioning, the Americans decided to have a new experiment, a new test, and this is called the Begrade. So they built on purpose a spacecraft as similar as possible to a real spacecraft, and they decided to fragment it. These are the characteristics of the Begrade compared to the old Sochi test. So it had MLI material, solar panels, and so on, and then they fragmented well above the fragmentation threshold just to be sure. And the test was actually performed. This is the mock-up, the design basically of a satellite. It was performed last year. And did they measure the velocity? What do you need to measure the velocity. The ejection velocity, the average ejection velocity of fragments can range from a few meters per second to 1,000 meters per second. So what do you need for catching the velocity? Very fast camera plus a very big room, because it's 1 kilometers per second. So you have to take several pictures possibly. So you need a fast camera and a very large room. You need a lot of money. So you take a camera, you take a fast camera, you take a large room, you shot your target. This is not the result. This is the much smaller experiment that Hanada and you made. You shot the target, bang, bang, bang. You have a very fast camera, you have a large room, and you don't see nothing. You see smoke. So you need a large room, you need a fast camera, and you need an X-ray camera, because you have to pass through the smoke. So they did the test, and they had no money, so they didn't put the X-ray camera. So they didn't measure the velocity. But the test was made actually. They showed us some result, of the result of the experiment, which is very impressive. They loaded giant trucks of boxes full of fragments, and they recorded all the fragments with all the possible materials, and they moved it to another location. And now they have to hire a lot of students to make their thesis counting the fragments and deriving the distribution. But they already say that the test was sponsored also by the Department of Defense, so not all the results will be public. So we are again in the same.
And how they can be sure that when they measure the sizes, that this is the real original sizes of the fragments and not after the collision with the wall? Because
the wall was soft, but yes, there might be. I'm not an expert. That the wall was soft and the room was pretty big, but probably not big enough to avoid fragmentation against the wall. But they as I learned, they had soft walls, and they took the wall in the trucks to examine everything. So that should come out, and the results, now they don't have money to analyze all the figure apparently. So the money is, they are asking for the money.
If I remember correctly, the experiments by Fujiwara in the 80s, they've been comparing the debris found after the hypervelocity impact with the things on the images. Trying to fragments on the images and then found them in the collection. And then if they were the same, then they said that they have identified something.
but in this case, they can't.
Well, they have a lot of images apparently, but they don't have images that allows them to track the fragment and measure the velocity. They have images, of course. Yes?
How do they collect the fragments and measure them? Do they have a standard setup? How do they collect the fragments?
I don't know. I guess they just clean the room.
They just clean the chamber, because how do they know? Do they?
Where they went, the direction you mean?
If you have the camera, probably you can see the velocities. But if you have also the lasers, as you say, probably they can measure them from the lasers. How do they know if they don't have secondary fragmentation from the sample?
Yeah, I don't know that. As I was mentioning, I don't know how they did that. Well, yes, they did some tricks, yes, to know where the fragments was coming. They use different materials, so they know that basically some clever tricks to identify fragments from the region they come from. But
You said we need a big chamber, and I agree, but did they also have it like a vacuum chamber? Or was it?
I think it was not. It was partly vacuum, but I don't know if it was completely. complete vacuum Simon chamber. I don't know if they say that they so if you have a new experiment to propose, they desperately need it.
I have an historical question. Recently, the graduate students in our department found a box containing fragments of fragmentation experiment from the 1980s on the box. You cannot throw them in the dust. Count them carefully before doing that.
Well, you can keep for the museum. Yeah, yes, Giblings. Well, actually, in the Astor, yes, as Zoran was mentioning, in the Astor, this kind of tests were made well before. They were all public, so.
So our group is so
And they actually measured the velocity, they measured the shape of the fragments.
the system that we still have to respond after 30 years.
So, I just have a question because it feels to me like there's a gap in the data. There is the breakout model, which is very statistical in nature and calibrated with a lot of ground data, and then you have these experiments in vast rooms. But I'm wondering the bit in between where you have high fidelity simulations with even CFD, whatever else thrown against, you know, an accurate model of a spacecraft, whether that doesn't provide any information on fragmentation processes. I would assume that we have for the physics, we have a basic enough understanding to be able to do high fidelity stuff as well.
Yeah, there are. This is a problem. There are no actually high fidelity. There are no high fidelity models like hydrodynamic codes or to simulate the fragmentation of a spacecraft. At least no publicly, no unclassified models. And it's something that the space agency should, in my opinion, I push because I push, for example, for ESA to develop this kind of numerical codes. But they are, of course, extremely expensive to do, unless you want to do a naive thing which is not very useful in the end. It's very expensive to write this kind of codes with meaningful physics, taking into account the complex structure of a spacecraft. But no, there are no software models which allows you to simulate things like they do in the asteroid population, for example, the PD-graph code or the CFH models.
Why did they use these foam panels for shortcuts and they need X-rays, high-speed cameras, while they could use ballistic gel all over the walls? So you don't need cameras, you have direction, you have penetration depth.
And then you need an army to analyze the data.
Because you know the mass of fixed process.
I'm not experimental.
Gel, this kind of camera is
On the big sensor. I don't think it's more expensive than X-rays high-speed cameras.
And you have a smaller room.
1 meter thick ballistic gel all over the place should give you something more than smoke.
then you have to open the gel and
Yes, but you see it's flagging how far in it went. You know its mass, so you can infer its velocity.
you have 10,000 fragments, what 9 hours to do.
They still took them from the foam, but the foam was just like a cushion. It didn't give any information. The ballistic gel will give information.
Anyway, and the takeaway message is that they in the future they will have one experiment, but again it's a single experiment, and as was mentioned, if you don't have a tool, for example, a software tool, which allows you to go from this experiment to an experiment where you have a non-central impact, an experiment where you have a modular spacecraft and so on, you will still rely on a single experiment and you won't have a physical understanding of more complex situations. So there's still uncertainties to be dealt with.
Okay, let's take to our